Helps. All righty. Well, look at this, not standing room only yesterday. I don't know, I feel some sort of way. Yesterday it was like people standing on a wall, and so now people are seeing, I'm like, do you want to see us today? Great. I hope the conference is going well. Welcome to the second day of ARPA-E. I'm excited for this session. This session is called Creating Tomorrow's Materials. I'm Dr. Cory Phillips, and I got an esteemed group with me here today that we're going to touch on our thoughts about what the next generation of materials can look like. A few housekeeping rules. So this year we're a little more fancy. We have an app with a code, and you can download this app. And when you get into this app, you can actually pick the room that we're in this morning, and then you can send us questions. You don't have to wait to send the questions. You can go into the app, click your questions, and then we'll be able to talk about those questions once we're finished with our fast pitches. And this is our way of sort of connecting with you early. And you can do this throughout the entire session. Today, we're going to do 4 fast pitches. I'm actually included in one. I'll be your moderator today. And these fast pitches are about 8 minutes long. So it's not a lot of time. The purpose of the fast pitch really is to engage and to inspire. We're trying to build communities. We're trying to give you the insight into what we're thinking about. And we got about 8 minutes to do it. So it's not a technical lecture where we can get into the depth. But hopefully, when you talk to us in the hallway later, you see us, we can sort of give you a little more insight technically on what we're thinking. We also want to promote collaboration. It's important that we do this. This is a time for us to come together. You took time out your schedule. You spent money to come down here and get together with us to see what is the future. And we want to share that with you. So our purpose is to talk about these materials and our thoughts, do that in about 30 minutes or so, and then we're going to have a call to action. We want you to meet us out in the hallway and share your thoughts with us on what do you think materials could look like in the future. So today with me, I have my friends and my colleagues, my esteemed friends and my colleagues, Dr. Julia Greenwald, Dr. Bob Ledoux, and Dr. Ryan Chaban. And we're here to talk to you about materials, and Dr. Greenwald will step up first and share a little bit of her thoughts about non-fluorinated polymers for use in electrochemical applications. Thank you.
Thanks, Cory. So today, I want to discuss why we need fluorine-free polymers to achieve our net zero goals. In short, why we need to get the F out. To hit net zero by 2050, we will need to increase our production of hydrogen, batteries, and carbon removal technologies. And we have set ambitious targets for scaling each of these industries multiple orders of magnitude in just 25 years. And at the heart of many of the strategies we're relying on is electrochemistry. This is the process of using electricity to drive chemical reactions, and vice versa, using chemistry to generate electricity. And as we seek to electrify everything from industry to transportation, electrochemistry is going to play a bigger and bigger role in our lives. We in this room have already bet big, investing more than $200 million into electrochemical technologies across more than 6 different ARPA-E programs. And as the name of the session implies, we're going to need new materials to meet these demands. So we'll need critical minerals for battery electrodes like nickel and cobalt, and platinum and iridium for electrolyzer catalysts. But what I want to talk about today are critical polymers. And these are the materials we need for binders, separators, and membranes within the devices. But many critical polymers are fluoropolymers. Fluoropolymers are derived from fluorocarbon precursors, small molecules with very strong carbon-fluorine bonds. And these bonds make them extremely stable and able to be used in harsh chemical environments. The fluorocarbons can be made into longer fluoropolymer chains that have those same favorable properties. They're water-resistant, inert, and can be used in these harsh chemical environments. They're commercially sold as products like Gore-Tex, Teflon, Nafion, and really essential. But they're also harmful. These compounds belong to a class called PFAS, or forever chemicals, and they persist in the environment for long periods of time and can be harmful to human health even at very low concentrations. So if we want to be able to rapidly scale electrochemistry in the short term, we're going to need to come up with safe fluorine-free alternatives. And now let's dive into one example. If we think about the hydrogen economy, hydrogen fuel cells combine hydrogen and oxygen to create electricity and water. This process can be very efficient and doesn't produce carbon dioxide. Fuel cells can be run in reverse to create hydrogen in a process called electrolysis. The most compact and energy-dense fuel cells use proton exchange membranes, which are made from fluoropolymers. The Department of Energy indicates that we will need 1,100 gigawatts of fuel cell and electrolyzer capacity in 2050, and more than half of this will come from proton exchange membrane devices, creating an associated more than 200-fold increase in our demand for fluoropolymers. We will need more than 20 million meters squared of fluoropolymers just for those proton exchange membranes. And the specific polymer we use is perfluorosulfonic acid, commercially sold as Nafion. It has a Teflon backbone and sulfonic acid functional groups. To understand why it's so widely used, we can zoom in on the membrane. Hydrogen enters the fuel cell from one side. It reacts at the surface of a catalyst to be split into two protons. The protons flow across the cell, and electricity flows in the external circuit. Then, on the other side, the protons combine with oxygen to form water. And we really use these materials because of the strength of the carbon-fluorine bond. This is the chief reason. They're really chemically stable. Additionally, the Teflon backbone is really flexible. And so this means that the polymers are mechanically robust. They bind easily to the catalyst particles in the electrodes, and they can tolerate large changes in volume, like swelling, during fuel cell operation. And then, of course, it's the sulfonic acid functional groups that form ion channels that facilitate proton transport. And the more hydrated these ion channels are, the more conductive the polymer is. But it wasn't originally designed for fuel cells, so it does have a few drawbacks. This polymer was designed for the chemicals industry in the 1960s, a different application. The chief drawback is that we can't use these polymers at high temperatures. If we could increase the temperature at which we run our fuel cells, we would be able to run them more efficiently. Additionally, the membranes suffer from limited lifetimes and selectivities. Membrane fouling is really a chief failure mode for fuel cells. And then the high cost contributes to why proton exchange membranes are more expensive than competing technologies. And of course, if we want to be able to do things safely and rapidly, we're going to need to come up with fluorine-free alternatives, especially in the face of increasing regulation of these materials. There's a lot of properties we need to optimize for when designing a new membrane, and it can be difficult to keep track of all of them. So we can plot the relative strength of each on a radar plot. And if we do this, anyway, if we do this for a particular polymer, like let's say perfluorosulfonic acid, what we can see is that the relative strength of each varies. It's extremely chemically stable and electrically insulating, but there's room for improvement in terms of its thermal stability and selectivity. So what that really says is that there's an opportunity to engineer performance improvements into the design of new materials. And one strategy that has been proposed is we can look at hydrocarbon-based polymers. Those aromatic backbones have a higher density of sulfonic acid groups, which means that potentially they can be higher conducting. If we plot ionic conductivity versus humidity, what you see is that the hydrocarbons can be even higher conducting than the fluoropolymers. But ideally, you want to run your fuel cell under more ambient-like conditions, so our target material needs to be high conducting at lower relative humidity. And conductivity isn't really enough. We want to think more broadly about stability. And so we want to make sure that these polymers don't crack at high temperatures or under dry conditions, and that they're really robust. We also want to make sure that they're more selective to mitigate membrane fouling. And, of course, we want them to be able to bind well to the catalyst particles in our electrodes so that we can form these very stable membrane electrode assemblies. And we want to do all of this with scalable manufacturing techniques like roll-to-roll manufacturing that will enable us to move quickly and economically. In this talk, I've really focused on the hydrogen economy, but I think it's important to remember that proton exchange membranes are widely used in other applications as well. So certain types of long-duration batteries also rely on proton exchange membranes, as well as electrochemically based carbon removal technologies, and fluorine-free polymers are really needed. And given how well the fluoropolymers work, it can seem daunting to try and come up with an alternative. But we've replaced hazardous materials in the past. Lead pipes don't rust, but we came up with other pipe materials that don't rust as well. Asbestos is really insulating and fire resistant, but we came up with other materials to insulate our homes with. So there's no reason we can't do the same for fluoropolymers and start with proton exchange membranes. So if you have ideas on how to do this, I'd love to talk to you. You can come to Coffee with ARPA-E tomorrow or email me at the address shown here. And now Cory is going to tell you about the future of catalysis.
Awesome. Thank you so much, Dr. Greenwald, my friend Julia. So I see the clicker has a mind of its own, so I'll tell the audience before. Whatever the clicker wants to do, that's what I'm going to present today. Quick question for the audience. So if I told you, or if I asked you, what did you think if I said that we could build or design chemical processes on the order of months instead of years? Would you think that, would, by a show of hands, would you think that would require a lot of magic? So I see I have some people in here who have actually been involved in that. Yeah, it would, actually. So, this is Tinkerbell. And I'm Cory Phillips, and I want to talk to you a little bit about what I call pixie dust, or what the technical term is, magical pixie dust. Or what really this is about is advancing and accelerating catalytic material design, discovery, and deployment for energy. And when we think about this pixie dust, when I was at the refinery years ago, the operators, they used to call catalysts, and the class of catalysts I'm talking about today, heterogeneous catalyst, pixie dust, because it really is really magical in how it can convert things from one reactant to a product and the actual technology that goes into that. But more importantly than that, is that these chemical processes and these energy technologies of the future that we actually want to design, you can't do it a lot of times until you have a catalyst. And that's extremely important. So in the room today, I know there's a bunch of you out here today that have great ideas on, man, I wish we could just take this feedstock and turn it into this product. I just need to figure out how to do it. I need a catalyst. I want to talk to you because we're going to need a bunch of new catalysts, and this is what I'm going to tell you about here in a sec. So for the broad audience, maybe you're not familiar with catalysis and what I'm talking about today. Just imagine that you have some feedstock. It can be water, biomass, ammonia, you name it. We'll just call that A, okay, some A. And we need to transition A to B. All right, generally, if you look at this plot here, relative energy, or reaction coordinates, or the direction of the reaction, A starts off with a certain amount of energy, and then you have to give it some type of energy to make this transition, and we call that an inherent activation energy. Has to cross that threshold, and there's a transition state at that threshold, and then it goes to a product B. Very straightforward. And this can happen without a catalyst for many reactions, and for most reactions, though, you need a catalyst. And the class of catalysts that I'm talking about today are these solid catalysts called heterogeneous catalysts. It's a field that's been around over 100 years, actually. What's special about this is that A can actually absorb on the surface. This is how it works. And it forms these surface intermediates. And these surface intermediates can then transition, just like the homogeneous case, with a lower activation energy. And it's this lower activation energy and this lower energetics of these transition states on the surface that allow you to form this product B on the surface, which eventually desorbs. So for the catalyst community in the room, they're probably thinking, Cory, you make this really simple. But I have a broad audience today, so I want to basically introduce the concept. But what I really want to stress is it's not just about speeding up chemical reactions like we learned in the past about catalysts. It's really about enabling chemistry that would not take place unless we had that catalyst. And when we think about the energy that we use right now as society, these are important materials. You take a refinery. A refinery has about 29 quadrillion BTUs of energy in the US that comes out of it, overall, just for the US. And it's done by this class of materials. They come in different shapes and sizes, depending on how you want to engineer the mass transfer and heat transfer for your reactor. But it's millions of tons every year that we use. The global market is about $5 billion just for refining alone. If you take the average cost of an FCC catalyst, you're looking at landfills, 7 large landfills, 7 piles of pixie dust, piles and piles of pixie dust that are required. Why is this important? This is important because if we really want to go to our net zero emissions goals and our targets, it's going to require millions and millions of tons of new catalysts for all the new chemistries that we're going to need in the future to meet these emissions targets, which are really difficult. A lot of difficult chemistry out there, and there are companies in the room right now working on this, so you know exactly what I'm talking about. This is going to be a huge challenge to replace all of that 29 quads of energy. So we're going to have to work together as a community. So what does this mean? This means we're maybe going to have to change the way we develop and design catalyst materials. We're going to have to speed up the process. We're going to have to change our workflow. So what do I mean by workflow? Well, when we're designing a catalyst, when you look at the journey of a catalyst, it really begins in the mind of the researcher. You have some anecdotal evidence, maybe some hypothesis, rational design premise on what the active surface looks like on the catalyst or your desired catalyst, or the desired reaction that you're choosing to have. So in the mind of the researcher, you're reflecting on the literature, you're reflecting on your own experiences, you're thinking about what surface alchemy with respect to the metals that you need to make this happen, and then you go out and you purchase those precursors, you read a little more literature, a little more patents, and you come up with some synthesis methods, and this is on the order of days and months, and eventually you come up with your own pixie dust, your own powder, your own active powder. But at that point, that's all this is. It's just a nanostructured powder. You don't know if you've actually created a catalyst or not. So in this scheme, you need to go further. And when you go further, you really get into the field of catalysis, which at the core is synthesis and characterization to understand the structure, property, and activity relationship. And you use these tools, remember that tools, I want to stress tools. This community has used tools and sophisticated characterization tools over the years to really understand how to do this cycle of rational design. How do you do this better and better? And how do we incorporate more tools and make them more widely available? So things like scanning electron microscopy used to be, back in the day with the EDX, electron dispersive cell on there, you had to go to a specialized subject matter expert and you had to schedule time. These tools now are becoming commonplace and they're on the bench top. So this community knows about tools and what it takes to really understand these surfaces, but we need to do more for this workflow. That's the rational design community. The commercial design community, they're interested in taking these powders and actually converting them into composite materials that actually combine binders and other additives in there to form engineered forms of materials. Things like structures, extrudates, wash coats, things that you find in large reactors, like I mentioned in a refinery. And they have a different goal. They're trying to actually make large tons of this, so the scales are different. These two communities, though, are not in communication as much as they should be in terms of actually a single workflow. And we need to figure out how to bring them together to share more knowledge more easily and actually help this time frame in the workflow of 20 years. If you start from the beginning of the concept of rational design all the way to loading a reactor, that's a long time. We can't wait 20 years. And the reason why we can't wait 20 years is because these targets that we're trying to reach are here, they're in front of us, and they're going to take a different way of doing things. We think that we need techniques to really cross the length scales in a way. We need tools that will enable us to get across these scales and test in lab scale to commercial scale. So can we connect the lab scale testing across the length scales and do it in a way that allows us to mimic what's happening at commercial scale, using some proxy type of devices or reactors or surrogate reactors or devices, both on the electrochemical side and also on the thermochemical side. So if you're using electrochemistry, can we test MEAs instead of just testing the active powder? Can we test at the MEA level? And can we test hundreds of them at a time? Can we do it in a way that's fast and high throughput? But it gives us an opportunity to see what's happening at a commercial scale. So that similitude between lab and commercial. Can we do that now? And we need tools to be able to do that. But when we test and we do the rigorous modeling at lab scale on what's happening at the commercial scale, then can we make these surrogate models to help us do it faster? So we need to cross these length scales, and we need to do it fast. What I'm asking the communities out here today is consider this. If we had a closed loop workflow where you have a guess, a way to do the computational chemistry to guess your initial elements that you need for that active surface. And you make that guess, and we do it faster. We use surrogate models, not necessarily the hard, rigorous ab initio for every single situation, but eventually develop those models that allow us to get us in that space. And we get us in that kind of space that then allows us to give us an idea of where we can test and explore, using maybe autonomous laboratories, self-driving labs, parallel testing platforms where you are testing maybe tens or hundreds at a time, but doing it in a way that enables us to connect across the scales and do it fast. And eventually, if we can take this data, this characterization data, the synthesis data, the testing data, and actually apply optimization algorithms of your choice. If you want to do neural networks, Bayesian optimization, if you want to do multivariate statistical optimization, whatever allows you to automate database and generate a database and automate that into some type of models to feed back into the initial guess. We think this closed loop approach can really accelerate this. So if you're here today and you believe this tool can happen, you share the same vision as I do, and we can make this tool widely available to the broader scientific community. So this particular field of study can really accelerate what we're trying to do at Net Zero. Come talk to me, okay? And let's talk piles of pixie dust together. And I'll tell you a little more about Tinkerbell and what she can do as well. Thank you for your time. And thank you so much. And next up, I want to introduce you to Dr. Bob Ledoux, who's going to tell you a little more about a different scale, the quantum scale. Thank you.
Thank you so much, Cory. It's always good to start the morning with some magic. And thanks so much of you for being here. Today, I'd like you to imagine the future in which essential problems in chemistry and materials are solved not in years, but in days. Quantum computing has the potential to do exactly that. Now, you may say that this is science fiction, Bob, but it's really not. Quantum computers today are actually doing simulations, and they're available for experimentation. It is the extremely early days in quantum computing. So just like in the early days of classical computing, it's absolutely essential that we tackle software and hardware problems together. And that's what I'd like to talk to you about today. Now, you know, this is one of the fields in which basically we know the theory, because chemistry and materials science are completely encapsulated in the Schrodinger equation. And we've known that for 100 years. That's not the problem. We've got the theory. The problem is that we have to use in classical computing approximations, because we can't solve this on a classical computer. So what that leads to is inaccuracy, and eventually that limits the predictability of these simulations. Quantum computing, by its very quantum nature, has the ability to radically transform this issue and allow us to accurately and rapidly simulate quantum systems. Okay, so how are we going to do that? Well, I think this was best summed up by one of the founders of quantum computing, physicist Richard Feynman, who said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical." And by golly, it's a wonderful problem because it doesn't look so easy. Richard Feynman grew up in Brooklyn. He had many, many clever ideas, and he was actually right. It is not easy. So here's the thing. What's the fundamental difference between quantum computing and classical computing? It is, in fact, the qubit. And the qubit itself, unlike a classical bit, which only takes 0 and 1, a qubit is actually a small quantum system. As an example, it's a spin up and down system. But the amazing thing is, qubits can simultaneously be in both states. This is called superposition. And this superposition is what allows, along with, we're going to see entanglement, the special properties of quantum computers. In fact, due to superposition, one qubit does not have to take on the values of 0 and 1. It can take on the value of any point on a sphere. There's more, and it gets better. Qubits can be entangled. And it's this entanglement with superposition that allows these quantum computers to do massive parallel computing when you simulate a quantum system. This illustration is just the information that can be stored in just 8 qubits. But here's the amazing fact. In just 100 qubits, you can, in principle, encode all the bits on all the computers on planet Earth. So that's the massive power that's contained in this. And this allows quantum computers to break the curse of dimensionality, which is the limiting factor in classical computing, whereas for even modest-sized quantum simulations, you need literally cosmological numbers of quantum resources and time to solve the problem. Okay, so we got a lot here to unpack. How are we going to make our way through this so that we can most rapidly realize the power of quantum computing? We're proposing, and that's part of our discussion with you today, that we really have to take a holistic approach. We have to go through the full quantum computational stack, which includes applications, software, and hardware, and we must co-optimize them now to get the full power of this. So let's start with applications. We want applications in which quantum computers make a difference. Our buddy Richard Feynman told us, simulating a quantum system. So check the box for chemistry and material science. We need to discuss which problems we want to solve and can solve first. Next, you need software to solve these problems. Now, given the nature of quantum computers, this software is really almost completely different than classical computers, because basically it's trying to harness the superposition and the entanglement to make it all work out. And presently, today, there is as many qubits as there are people in the room. That's an exaggeration. But there are many flavors of qubits. There's superconducting, there's photonic, there's negative ion traps, et cetera. The point is, there is no standard in the quantum computing. So we believe, and we'd like to discuss with you, you're not going to solve this by general purpose. You have to completely optimize the stack doing that. Okay, now let's take some applications. We heard a beautiful discussion, catalysis from Cory, and using all sorts of new techniques to make it better, but we would like fundamental calculations. So let's start with an example. This is direct air capture of CO2 mediated through a ruthenium catalyst, right? And you write these equations down, it kind of looks simple. But our present understanding is far from it. It's an extremely complicated process with many, many reaction pathways. Some include excited states. There are errors in every one of these in classical calculations. The point is, we don't have much predictive power. So what are we going to do in the near and the midterm? Well, what others have proposed, which leverages what Cory said, it's going to be a hybrid solution. You start with the power of what we know from classical simulations. You use that as a starting point for the quantum. So you get the orbitals, the electronic configurations classically. And then you shove those babies into the quantum computer, because it will be able to do those very, very important correlations rapidly and accurately. So for the foreseeable future, this is probably the loop we're going to take. And when you look at the quantum software side in this problem, it's very nascent, but I will say that in this problem of energy surfaces, in 1 decade, those solutions have been proposed that take 5 orders of magnitude less resources. A lot to be done, but a lot's been done, and we need to discuss how to move this forward. Now, my next example is superconductivity. I mean, come on, what we wouldn't give for a room temperature superconductor, right? It would energy transmission, fusion energy, like we want it. Superconductivity is actually old. It was first discovered low temperature in 1911. Wow. Okay, but it wasn't until 1957 that an adequate theory, the BCS theory, explained low temperature superconductor. Okay, it still took till 1987 to find higher temperature practical ones, right? And we're still debating today, some of you may disagree with me, we don't even know if the BCS theory explains those new ones. I would posit we don't have a fundamental theory of them. Therefore, it is extremely difficult to make progress. What we hope quantum computing can do is that it can understand both those short-range correlations, the Cooper pairs, as well as the long-range interaction with the lattice. They're both necessary to understand this problem. Quantum computing should be able to do that. Okay, so here's the call to action. We want to achieve this successes in quantum computing as quickly as possible, but how do we do that? So we've already proposed we're going to try to optimize the full stack. So here's the call to action to all of you out in the audience. What applications do we want to start with first? I mean, clearly we want important problems to solve, but what is it that we're trying to improve first? Is it the accuracy of energy calculations? Or it could be something much more exciting to me, a fundamental explanation of reaction pathways. Let the nuclei move, remove the Born-Oppenheimer approximation. But we need to come together as a community to really catalyze, use a pun, this field. Software, it's at a very nascent stage with a lot of progress. But again, we need to probably specifically write software now for specific applications. And with the uncertainty in what the quantum hardware is, which is rapidly evolving, I think we're going to have to take specific algorithms and always make them specific to the hardware for the time being. I believe this is a completely multidisciplinary process. I would love to work with all of you. We need application experts, software and hardware. To me, this is fantastically exciting and potentially completely transformative. And so let's start this dialogue here and beyond to figure out exactly how we do this, to do it as quickly as possible. And I think ultimately, I hope a few of you will take the quantum leap. And I look forward to discussing this with you both today, at the coffee tomorrow, and beyond. So I thank you very much for your attention. And now we're going to talk about some systems, material systems of a bigger scale. Ryan.
Thank you, Bob. Today, I'd like to start with the question. When you walked through the door this morning, did anybody think about the building collapsing on their heads? I know I didn't. And that's because we trust our built environment, and it is always an emergency when it fails. I'm Ryan, and I'm a fellow here at ARPA-E. And today I want to talk about how we can build the infrastructure for the energy transition bigger, faster, and safer. First, let's talk about why this matters. All energy infrastructure requires literal tons of materials, and these are often extremely emissions-intensive materials, concrete and steel. Concrete represents 8% of global greenhouse gas emissions. And every year, we pour enough of it to fill half the volume of Sydney Harbor. But even if we choose the lowest material-intensive form of power, nuclear, we still have a fairly rigid minimum to our material requirements. The real variable cost is time. Over the past 75 years, construction productivity has decreased by 30%. Meanwhile, the productivity of the overall economy has nearly tripled. And this slows things down. The very obvious example is large infrastructure projects. This is the Vogtle nuclear reactor that just came online last year in Georgia. It comes at a price tag $17 billion over budget and 7 years behind schedule. Part of this is because this is the first nuclear reactor we have built in 30 years. And in those 3 decades, we have fallen behind on the learning curve, and we've forgotten how to pour concrete with different additives like boron. And 30% of the concrete at Vogtle needed to be ripped up and repoured. So the way that we typically talk about decarbonizing construction or concrete is with a drop-in replacement that doesn't require us to change our materials or methods. But today I want to talk to you about how a drop-in replacement is small thinking. We need to look at the methods we actually use to qualify. So this is the standard flow for a material or structure. First, we design it, then we figure out how to manufacture it repeatably with castings, forgings, injection moldings, take your pick. Then we break it many, many, many times, and we build up some statistics. From these statistics, we determine a threshold and we determine a safety factor. And we certify it at that standard. This is a time-intensive process, 3 to 7 years for most commodity materials. Now, on a construction site, this is even worse because every individual pour of concrete must wait to cure, be cored, and crushed. Now, if this passes our certification test, then we're good. However, if the core fails, the entire pour needs to be ripped up, repoured, and reset. And when construction timelines are built to precision, a delay like this can push projects back months to years. It's also not that uncommon. 30% of all work done on construction sites can be classified as rework, according to some studies I found. Now, there are 3 key technology categories that can change this paradigm. The first is new building methods in additive manufacturing and new materials. So ARPA-E has made progress with the drop-in replacement in our Hestia program. We have demonstrated concrete chemistries with net negative life cycle emissions and cross-laminated timber nearly as strong as steel. Also, the ARPA-E high temp program has shown that we can additively manufacture metal into complex structures, and we can 3D print concrete in ways that we cannot cast using traditional methods. The second key technology is the invention of new sensors. Thermal imaging and thermal sensors can show us where heat may be pooling or concentrating and can help us make models. Also, machine vision can show us how we can precisely show whether an additive manufacturing structure is being built to specifications. Also, acoustic methods can show us if there are cracks deep inside our structures over very long spans in many different materials. And also, X-ray methods can show us microstructures and defects and voids and can help us predict the macrostructure stability. Now, all of these sensors, and some that I'm sure people in this room are working on, are going to create massive amounts of data. And with that data, a person cannot possibly analyze it, so you all know where this is going. AI will be the third technology that is coming into its own that can change this paradigm. Every step along this process, from material feedstock to embedded sensors, can feed data to a physics-informed AI that can help us make models. This brings me to my first call to action. We are not collecting this data right now. We need to develop a generalized information schematic according to FAIR principles so that we can train better models. And from these models, we can make better digital twins, which can help us predict the maintenance of our buildings and increase their lifetime, reducing the carbon intensity of their embedded emissions. Also, we can develop better control algorithms for our additive manufacturing and robotic construction. This fundamentally changes the paradigm from a one-way, slow procedure to a cyclical, real-time process where we build, sense, and control at the same time such that the final product is by definition certified. Now, what this paradigm does is it actually streamlines speed for current construction. We can 3D print our longest members on site. Every civil engineer and architect knows that the length of a standard truck bed is 53 feet, and they design around that constraint. If we could print our longest members on site, we can reduce the amount of crane time we have, and we can reduce the stick build parts by up to 30%. This lower part complexity is also directly linked to faster build times and lower rates of rework, increasing our efficiency. But this paradigm can move even further. Some of the largest infrastructure for the energy transition is not limited by the strength of our structures. The length of our wind turbine blades are limited by the roads we take to transport them to their destination, and the diameter of our towers is limited by the overpasses they need to travel under. With this paradigm, we can 3D print concrete wind turbine bases on site, having the embodied emissions of the steel in the tower, and we can weave carbon negative blades that can move to double the state of the art from 20 megawatts to more than 50. And finally, there are some things that can never be built in a factory. With this paradigm, we can fix and build the infrastructure that this country needs in a fraction of the time at a fraction of the cost. Now, if you are a construction junkie, a roboticist, a material scientist, or an AI expert, I would love to hear your ideas. Find me tomorrow at Coffee with ARPA-E or around so that we can build out the infrastructure we need bigger, faster, and safer. Thank you very much.
That was great, Ryan. Thank you so much. Got a few minutes for Q&A, if you all don't mind.
That's why we're here.
Okay. Had a couple questions come in from the audience, and I think Ryan, I want to start with you, if that's okay.
Sure.
So the question that I received says, why has construction productivity decreased, and how would the innovations you've suggested increase productivity?
That's a great question. So when I first saw that plot, I was actually shocked. And the question is actually easier to answer if you flip it on its head. Why has general productivity increased by a factor of 2.5? And if you think about that, what did we invent in the last 70 years that is now sitting in all of our pockets? The computer, right? Construction technology hasn't had a generalized productivity tool. And in addition, construction is a whole lot safer than it was 75 years ago. So between safety regulations, which are a good thing, and a lack of a generalized productivity tool, construction has fallen behind. So what this paradigm can do is it can empower the builder. Basically, for every single person, instead of 3 guys holding a beam as we slide it into place, you can have a robot holding that beam and 1 guy controlling it as it moves into place. And it becomes the ability, or it increases the ability of a single operator to do more tasks.
Oh, that's great. Thank you. Thank you so much. Bob, I have one for you. Could quantum computing perform a highly realistic and accurate simulation of reaction dynamics?
Oh.
Yeah.
Yeah, I love that question. I think that question goes to the heart of who we need in this audience to help us solve this problem. Because we want the application specialists now that really know what the juggernaut is in that reaction dynamics. I would say if you started with a clean sheet of paper, you would not do it in the way we do it now, that you would say, can I use directly the time evolution of the wave function to actually just measure as a function of time what the wave function does? In principle, that is the reaction dynamic. And if we could get enough resources and we could time evolve it, it's exactly what nature's doing. You're just looking at nature on the quantum computer. So it could be for catalysis,
yes,
but it would be the same thing for a photoexcitation. You would just be looking at the photon interacting with an atom, and you would just time evolve it. I think it's one of the holy grails. It might be a while before we get there, but that would be a game changer.
No, that's exciting because then it's the granularity at time scale and length scale that you have now.
It would be at femto scale.
Yeah.
Yeah, and it would also connect to diagnostics. Because right now we do a lot of photoexcitations and forget making something, just to look at them. And again, if there's many intermediate states and we look at the measurement, we're still trying to figure out what do we measure.
Yeah.
So it would help there too.
Thank you. I'm excited. So
Let's try it.
Appreciate that. And Julia, got one for you. So in addition to hydrogen electrolyzers and fuel cells, what else are proton exchange membranes used for in the clean energy industry?
Yeah, so I mentioned that certain types of long-duration storage batteries, like vanadium redox flow or electrochemical carbon dioxide removal techniques, but more broadly, perfluorosulfonic acid-based membranes were developed for the chlor-alkali industry, so to make acids and bases. So it's really an enabling technology for anything that uses acids and bases. So that's a very wide suite of our electrochemical future. And of course, also, as we try and move away from thermally based separations, I think you're going to see increasing dependence on using electrified separations, like, in sort of environmentally benign mining or things like that. And right now, all we have are pretty much perfluorosulfonic acids for proton exchange membranes.
It's definitely our future, and definitely a huge opportunity to do that replacement. Do you envision that all of it, or at least a majority, could be replaced in the future?
I wouldn't say everything, but I think that we sort of got lucky, and that like Nafion works really well in a lot of these things, but perhaps we haven't tried that hard just because it worked well to develop alternative materials, and we might have to develop more tailored materials for certain applications. And definitely within mining, oftentimes the ion of interest is not a proton. So you want to develop an alternative cation exchange membrane or something like that.
I know I got excited when I saw you present about the hydrocarbon opportunity. Think about, so many hydrocarbons that you can get, low carbon hydrocarbons that you can get to actually serve for that purpose. So that's an exciting future. One that I had for the entire group, and I can include myself.
How about one for you?
Yeah. This one might do it. So someone in the audience wrote, what are the biggest advantages of using AI in material science research? And that's for all of us.
Yeah.
So maybe I'll kick it off here. So there was someone else that asked a question also about, is there an accurate catalyst simulation predictions are the core issue? So that goes back to this AI question. There are two parts to what I presented that are important. With respect to like modeling and optimization and statistical modeling. The first one is at the ab initio level, we really have to develop the rigor to understand what we're doing on the surface, on the catalyst surface, like what Bob mentioned. But then there are surrogate models we can develop, which is happening now. But we need to really include in that data set, in that training set that we use for these models, those surrogate models, more metadata involving synthesis information. So coming out of that first, when I showed that closed loop cycle, coming out of that first closed loop cycle, we really need to have not only surface compositional information, but also is it manufacturable? So the materials that are suggested, not only are they synthesizable, can you synthesize them, right, coming out of ab initio, but can you manufacture it? Because a big part of what we're talking about here on my slides was tons of materials. You remember I showed the refinery and I showed like there was millions of tons annually that are using this. So coming out of that first guess, it has to be synthesizable and manufacturable materials. And then on the back end of that, when you're testing them, and you're testing them in a way that a commercial similitude where you can actually correlate to something that's happening commercially, can we actually build models there that actually capture the multi-physics? So all of the heat mass transfer at scale, and can you basically change the scale and have those predictions predict what you're seeing at the lab? I'll let Bob or Julia and Ryan kick in on what you think about them.
I'm happy to say something. I mean, AI, they laugh because I'm always happy to say something. I mean, AI is advancing at such a rapid rate, and it's so sophisticated in quantum chemistry. Oh no, it's the thing to beat, and God bless it, just go forward as fast as you can. And the other thing, I talked about what quantum computers were good at. What they're not good at is handling a lot of data. And actually, it's not proven purely for like machine learning if they're helping. So I think that loop that I showed you, that hybrid loop with a classical computer, AI is doing a lot of heavy lifting, but it just gives the part dimensionally and so on that classical computing just cannot do. And so I think it's a match, it's a marriage made in heaven.
Yes, it sounds like, and then you talked about dimensionality. Do you envision like, having so much dimensionality, but also having the power now to reduce it down to the important things that matter faster?
That's a great point, because until the quantum hardware really improves, it's doing still very high accuracy problems, but the dimensionality is limited. So another reason why AI is here to really do a lot of it still.
It's exciting. So Julia, right? Either one.
Well, I think trained as an experimentalist, and it wasn't that long ago that I did synthesis. I always have my skepticism of but I
Not
do.
you, Julia.
Yeah. But obviously, there's like great opportunities, obviously, in AI for materials discovery, and I also think especially with like robotic experimentation, so you can get really uniform data collection, really, as opposed to undergrads and variability and such. I think.
Did I just hear AI to replace
Out to all
undergrads?
you undergraduates.
Oh, that was me. That was me not that long ago. I was spending a lot of time trying to re-get things to crystallize. And so I think, with like robotic experimentation, then like you'll have really good quality data to do AI, and that'll be really great.
I like that point, though. You're basically saying, it can be an assist. It's really a tool. Oftentimes we view it as replacement, and it's really a way to advance our current scientific fields that are involved in heavy experimental work and modeling. So, Ryan, you just finished a great discussion on this. So,
I got 2 key points. So fundamentally, AI is really complex pattern recognition. It's insanely good at pattern recognition. But one of the things that we know is that as soon as you deviate outside of your training set, it gets really bad really fast, right? Catastrophically bad. And we can't have that kind of failure when we do construction. So the first thing is physics-informed AI. So you can build these control structures into your algorithm as you are training it. Your evolutionary algorithms, you can kill off the ones that don't have that are not sound according to the physics principles you were using. And then the other key advantage of AI is something called sliding autonomy. So the idea is you can have, if I tell a robot to go do something, it can have a different hierarchy of how much autonomy it's going to do. I can tell it to just pick up this thing from right here and put it right over there. Or I can say, grab me a 2x4. And it has to go look for the 2x4, figure out what the 2x4 is, and bring it back to me. And those are different levels of sliding autonomy, and they have different applications. And fitting the right autonomy hierarchy is important to figure out for safety.
So in your example, on the on-site additive manufacturing, you envision definitely having the capability to apply an AI principle in that scenario as well.
Yeah, absolutely.
Oh, that's great.
And also has to do with insurability, right? If I'm going to have a robot do an inspection, but there are certain inspections that I'm also going to have a human duplicate.
We call that expert in the loop, so we don't want to kick the expert out of the loop. I think all of us agree with that.
Yeah.
So I got one for Bob. It's interesting. So Bob, is there a Moore's law analog for quantum computers to measure progress, or are the approaches too nascent to compare at this point?
Oh, I think it's way too nascent.
Yeah.
I didn't point out, again, for lack of time, really the big thing is making qubits last longer, so to speak, reduce their error. And it's a combination of 2 things. People are getting the intrinsic technology to be better, and they're actually making error correction codes. And the other weird thing about quantum computers is you can't copy a qubit, because then you destroy it, and you destroy its coherence. So basically, I think the answer is no, we're a long ways from that. But you don't need a lot to do a lot. So.
Yeah, that's true. That's a good point. Yeah. Eventually, though, we'll be tracking and measuring how we're doing. So that's going to be exciting. And Julia, are there other types of fluoropolymers that are also important enabling materials? It's not like you're against all fluoropolymers.
Well, I mean, yeah, I think we're all very familiar with Teflon in our homes,
yes,
but then also in all sorts of, gaskets or sealants, the way that we transport liquid and gaseous energy, or also, you coat solar panels in Teflon, so that's another important fluoropolymer. Also, PVDF is widely used as a binder in a lot of lithium-ion batteries, so that's another fluoropolymer that we really depend on for energy infrastructure.
Yeah, to that point too, how do you ensure that the non-fluoropolymers have a lower environmental impact than the PFAS while still having desired characteristics?
I mean, there's no such thing as a free lunch.
That's right. That's right.
I don't know. I think we have to find out. I mean, we have to try first.
Yeah.
And identify materials, maybe using AI, and then once we identify materials that work, we should assess their environmental impact.
That's great. Yeah, it's going to be a journey, I'm sure, but an important one to take. If you don't take the first step, right, how do we know how to get there eventually? So, Ryan, what is the, this is interesting, what is the climate impact of using sensing and big data to improve certification?
The climate impact?
Yeah.
Good. There's
Real good.
real good. Yeah, there's two main impacts. One is we reduce our material usage, so that increases efficiency. It reduces the amount of embedded emissions in our materials. And the second one is we can build things out faster. So like to me, one of the scariest aspects of climate change is that it's happening now, and building things takes a lot of time. So the whole reason I pursued this idea is how can we rapidly deploy energy technology? And to me, this seems like a way that we can do it faster and we can bend that curve down faster. That's how I think of the climate impact of this technology.
Would a defect or a mistake made in an on-site 3D printed structure cause a greater rework? More times, more lost time, more segmented parts, which are currently in use?
That's a really good question. And actually, this paradigm isn't only useful for building things, it's useful for repairing things. So the idea is if we can sense the structure where a defect happened. So if we can catch the defect immediately, that's the best. If the next best thing is we find the defect but we can't repair it immediately, we go in, we carve it out, and we replace it using this exact same paradigm. And that actually decreases the amount of rework we have to do.
So there's a huge opportunity there just to speed things up and also save on cost. I mean, every time you have to do a rework, right, the costs and changes of that and change orders really mount up. And so that's how we got the issue with Vogels. Thank you. Mm-hmm. So Bob, would existing tools like density functional theory, DFT, necessarily be scrapped or adapted to cubics? You can't scrap DFT. Yeah. Come on, I need my heats of absorption.
We have probably a lot of DFT aficionados out there.
So all you DFT people out there, we're not scrapping this.
We love density functional theory.
We do.
We really do.
Yes.
No, it's an incredibly powerful tool. Look, I think classical computing shows the same thing. You don't give up very efficient, not completely accurate tools. You always start with them. And in fact, I would say that if you're trying to, survey a very large area of a new material that Julia wants to make or whatever, I think you're going to do it with the classical tools, at the lower enough burden. And I think you start there. And it'll be a long time before the quantum computer can really do all the heavy lifting. So, no. Keep those tools coming in. There's time-dependent, DFT, all that's being improved. It's a great competition. We love competition.
You do, and then you probably can imagine some emerging tools developing too, right? And emerging calcs too, once the power comes in, right?
Yeah.
So to enhance what we've done in
exactly.
DFT, right? So
yeah.
I think 11 o'clock's our time. Right?
All right.
All right. So audience, I really appreciate the engagement. We had a lot of questions come through. I couldn't get to them all, but please join me in thanking my panel here today, and thank you for your time.